Hey, I'm Liam, and this is my final SAR ADC build. If you don't know, SAR ADC stands for Successive Approximation Register Analog to Digital Converter. So basically what this does is this circuit takes in a reading from this potentiometer between 0 and 5 volts and spits out a digital value on those 7 LEDs that you can see. You can see that if I turn the potentiometer, the value on the LEDs will change. So it was at 5 volts there, and I can turn it all the way from 5 volts down to 0 volts, and then all the LEDs will be off. So, for example, if we take some random voltage, this is the digital approximation that the ADC comes up with. Using a DMM, we can figure out the real voltage at this point. So this voltage is 2.17 volts. And the digital approximation of this voltage is the binary number 0110111. With the demonstration of the working circuit, let's go to a bit of an explanation of how to interpret this result, because it may not at first be very clear. This resultant binary number can be thought of a fraction out of 127, because the highest possible value on the output is 1111111, or 127 in decimal. This fraction represents the ratio of the current voltage being read to the voltage range, which is 5 volts. So, right now we see that the number 55 is on the output. We now take this as a fraction of 128 and multiply this number by 5, and we get the output voltage. As you can see, this is pretty close to the actual voltage read on the DMM. It's pretty hard to show what's going on in this circuit by just using LEDs and DMMs, so a better tool to do this is looking at the oscilloscope. Here's an image from the oscilloscope looking at the output of the DAC. As you remember, the DAC is used to essentially guess what the input voltage is. You can see as the cycle of the SAR continues, the guess from the DAC is more and more accurate. To check the actual output of the ADC as an analog value, we can simply run the 7 output bits through another DAC. We can then read the output of this DAC and compare it to the input voltage. As you can see here, we're following a sine wave with the output of the ADC. This produces a discrete representation of this sine wave with many different voltage values. You can also see here how there's a bit of a phase shift in between the two waves because it takes time for the ADC to gather its data. Correcting for the phase shift, as I've done in this image, showing that the output of the ADC is actually quite accurate to the input voltage.
Okay, so the final thing I wanted to discuss in this series of projects for the ADC is exactly how it works, scrutinizing one bit at a time, and how that works in circuitry rather than just in theory why that would work. So to do that, let's run through a approximation. For this approximation, let's just say that we have 1.75 volts as the input voltage, so this is 1.75. So we have our 1.75 input voltage, and on the first tick of the new cycle, we know that we have a 1 on all the outputs of these flip-flops here. So we can write a 1, a 1, a 1, 1, and so on. You get the idea? So on the first cycle, what we do is we set this AND gate high because we have a 1 here and we have a 1 from 5 volts. So we have a 1 and a 1. So that results in 1 here, which results in 2.5 volts here on this comparator, which will generate a high here. So we'll get, which will generate a 0 here. So we'll get a 0. And then this takes us to the next clock cycle. So let's go to the next clock cycle, and with this 0, we now have a 0 on the data, and then we have a 1 that's generated because this shift register shifts a 1 through from this V+, and it goes through from Q0 on 1 to then 2 on the next cycle to then 3, then 4. So let's go and see what that affects. So we now have a high on this, which is the clock pin of this first register, of this first flip-flop. So this updates the first flip-flop, and since there's a 0 here, this 0 is shot out and it gets to the other side of the flip-flop. So on the other side of the flip-flop, this one now becomes a 0. So then we have a 0 on this AND gate with a 1 up there. So then it updates and there's a 0 on this resistor here, which means that there's no longer 2.5 volts being generated by it, which is half of the supply. But with this new clock cycle, we also change one other thing, which is this one goes high. So we now have a 1 here, which means that this AND gate, which now has a 1 and a 1, generates a 1. So this one goes out onto the DAC, and this is half of 2.5 volts, so we have 1.25 volts here. And 1.25 volts is less than 1.75 volts, which is our input voltage. So we then get a 1 on this line over here. So that brings us once again to the next clock cycle, where we can go over and we can see that we have a 1 on this data line, and because now we have number 2 going, that means that this 1 gets shot through and it comes out to here onto this AND gate, which then makes this a permanent 1 set in stone. So there will always be this 1 on in the DAC. What that also means is that there's now a 1 because this 2 got set high over here. This means that we now have a 1 on this AND gate, which sets this bit of the DAC. So we now have 1.25 volts plus half of 1.25 volts, which is 0.625 volts here. And then if we add those two voltages, we're going to get 1.8 something volts on this output line. Anyways, that's greater than 1.75 volts, so we're going to get a 0 here. And then we go to the next clock cycle. That's going to set this to permanent 0 here on the DAC, and then we're going to test this bit, and so on and so forth. This process repeats until we set every bit. I don't know what they actually are, but until we set every bit on the DAC. And then by setting the bits in the DAC, we store them in this successive approximation register, which is really these D flip-flops here. And then on the final tick, on the 8th tick, what we do is we store the data that's coming from the successive approximation register, and we put it into this register that we have here, which then goes out to the output LEDs. So that was a bit fast, but hopefully that demonstrates a bit better how each cycle works and how we actually only scrutinize one bit at a time. Because, well, I explained in an earlier video, I didn't explain it with this specific hardware, and I think it's very interesting how this circuit does it, because it's quite smart. Anyways, that's about it for this video, so thanks for watching.